All right, so today we're going to be talking about quantum numbers here, and really it's just another way of indicating where an electron is around an atom. So there are four quantum numbers. I have them all written here with what they indicate. You can pause the video and write them down, but I'll go through them quick here. Essentially, we've got a principal quantum number, n, that is designating the energy level of an electron. It can have positive integral values 1 through, well, right now 7, because that's how many energy levels there are available currently. The next one is the angular momentum quantum number, L. It indicates the subshell of an electron, and it can have values of 0, 1, 2, 3. And those values are also based on n, and it has a value of n minus 1 or 0 through n minus 1. Right, so like for example, if n equals 1, the only value L can have is 0, but if n equals 4, right, it can have values of 0 through n minus 1, so it could have all of the values, right, 0, 1, 2, or 3. Then, after that, you've got the magnetic quantum number, m sub L. This indicates the orbital of an electron, and it can have values of negative L through L. And then the last one, your spin quantum number, m sub S, used to differentiate two electrons in the same orbital. It can have values of positive 1/2 or negative 1/2. M sub L, let's go back to that one for a second. So in this case, right, if L was equal to 0, M sub L could only have a value of 0, right? However, if L is equal to 3, right, M sub L could have values of negative 3, negative 2, negative 1, 0, 1, 2, or 3. All right, so that would be 1, 2, 3, 4, 5, 6, 7 orbitals. And if you look, right, F, if you remember, F has 7 orbitals available, can hold 14 electrons. Checks out. Okay. So the rules, there are some rules about quantum numbers here. We can thank this fine gentleman here, Wolfgang Pauli, for the Pauli exclusion principle. And basically what it says is 2 electrons in the same atom cannot have an identical set of 4 quantum numbers, right? And if you think back to the orbital notation electron diagrams, where you've got only 2 electrons in any given orbital, right? Essentially that is what this is talking about, because you can only have 2 electrons in any one orbital, right? And the spin values are going to be different. So you could have the other 3 quantum numbers be the same, but that different spin number is going to indicate positive 1/2 up arrow, negative 1/2 down arrow. So orbitals can only hold maximum of 2 electrons. No 2 electrons in the same atom can have an identical set of 4 quantum numbers. So quantum numbers, what they do is define the state of one electron around an atom rather than providing information about all the electrons around an atom. As a result, the same 4 quantum numbers could apply to an electron around several different atoms. Like, for example, this set of quantum numbers, right? So we have n equals 2, which means that we know that this electron is in the second energy level. L equals 1, which means we know that this electron is second E. L equals 1, so we know that this is in a p orbital. Then we have m sub L equals 0. this is more or less assigned randomly. There's no real reason why this couldn't be -1 or +1 as well. We're going to assign it arbitrarily. Same with m sub s, the +1/2. It could just as easily be -1/2. And if you're only talking about one electron, it won't matter, right? What we've got here is second and p, right? So this could be saying, what would the question that this set would answer would be something like, what are the 4 quantum numbers associated with one of the valence electrons in carbon? What would the 4 quantum numbers be that would represent one of the valence electrons in fluorine? What would the 4 quantum numbers be that would represent one of the core electrons in the second energy level of sodium, right? So you could answer, these 4 quantum numbers would be the answer to several different questions. We can work through some of these in class just to get you used to how this works. It's not too tough. It's pretty straightforward because you have energy level, subshell, and then some arbitrarily assigned values for m sub l and m sub s. So what's with these orbitals anyway? In the quantum model, if you remember from our history of the atom video, the shapes of atomic orbitals are based on the probability of finding an electron around the nucleus. And the orbital shapes are referred to as a probability density and are calculated using the Schrodinger equation, right? This guy here. Thanks, Erwin. These are pictures of the orbitals, right? So a lot of times they look pretty clear here like this. These here, these fuzzy diagrams, are actually a little better and slightly more accurate because it's just as you get further from the nucleus in a lot of these, the probability of finding the electron decreases, but actually never goes to 0. So there is a chance of finding an electron infinitely far from the nucleus of an atom. But anyway, this is what s orbitals look like based on probability. This is what p orbitals look like based on probability. Some d orbitals based on probability. And then f orbitals based on probability. So all of those mathematical functions that the Schrodinger equation gives you, this is the shape that is created by graphing those probability densities. All right, that's it. Thanks for watching this one. I'll see you in class.